Before we go into how a regulator works, it's important to know just a few safety aspects about compressed air or CO2. First of all, anytime you hook up a regulator, you need to test it with suds from soapy water. Not the water itself, but the suds. So create the suds and test it. Second, CO2, while not toxic, as in it'll poison you to death, obviously, if you're in a confined space and you had a really big tank and CO2, and this would be hard to do, but remember, you can't breathe CO2. It will kill you if you deplete the quality of the air in a small confined space. Again, not a big issue with the kind of leaks in tanks that we have, but you got to know that. And more importantly than both of those, anytime you're dealing with something with compressed air, you don't want to modify. We're your modified valves and things here, but you never want to do that. Don't take these things apart. You're going to void the warranty. You won't know how to put them back together. Just like a valve from a regulator, scuba shop, or whatever. You're not allowed to mess with your regulator, and there's a reason for that. Anything under high pressure can explode and kill you if it isn't put back together right. If it's a low quality item, it could be dangerous if it's not built right. And then CO2 itself, when it comes out, that's how you create dry ice. So if you've got a fast leaking valve here, I mean, you don't want to go and grab that with your hand. At negative 110 degrees, you can kill skin cells. So it's crucial not to touch anything like that inadvertently because it is very cold. Okay, with that being said, let's move right in to the valves themselves. All regulators, the basic function they provide is they take your tank pressure, which is constant on CO2. It'll stay in the 800 to 1,000 PSI range coming out of the tank. It reduces that pressure down so that you get to a workable PSI or pressure that you can use to power any of your diffusers or devices. Otherwise, if you used all of that pressure, your hoses would blow, your tanks would blow. It just wouldn't work properly. So that's the point of it. Choosing a regulator, and do you need one, first of all? There are lots of different types of aquascaping and planted tanks. For the most part, anyone that wants to do an upper end or really, really nice aquascaping tank is going to want a regulator. They're going to want CO2. There are exceptions to that. You can do low-tech tanks. You can do tanks with low-light plants like Anubias that have enough CO2 coming from the fish and the waste that they do okay. But for the point of this, and in all systems, the addition of CO2 will benefit even those tanks. So yes, you can do a low-tech planted aquarium without a regulator, but for anybody wanting to do the best of the best, if you will, or really have that, what you see, screaming aquascape, we're just going to assume for the purpose of this that you will want to buy a CO2 regulator. Now, picking one out can be confusing and complicated, and there's lots of different features. How much should you spend? You know, what features are you looking for? And that's what we're going to dive into. And first, we're going to start with how the regulators actually work. If you don't know how they work, and then all the different feature choices, you can't make the right decision for you. How the regulator works. A pressure regulator is comprised of three main elements. A pressure-reducing restrictive element or control element. Often this is spring-loaded poppet. This is an example of a poppet. So this is a balanced poppet design. You can see the small hole here. Shows you the balanced poppet design. It's a spring, and the poppet moves up and down on the spring, which will actually presses into there. That's the air filter coming in. And then on this side, this poppet will come up to close the orifice, the small hole, before it comes in, it's going to push against the diaphragm or the spring. So this goes up into the hole to determine the pressure of the CO2. A sensing element, which is typically a diaphragm or piston. This is an example of a piston. This is a piston. We go back and forth. They can be made out of this type of material or brass, sometimes stainless steel, typically brass. A reference force element called a loading mechanism, which is most often commonly a spring. So there is the loading mechanism, the spring. The opening of the valve applies pressure to the sensing element, which in turn closes the valve until it is open just enough to maintain the set pressure. Features and what affects function of CO2 in different applications. Body type. There's lots of different body types of regulators. Everything is out of some sort of machine stock, or it's formed out of brass, stainless steel, aluminum, and coated. This is an example of a heavy-duty brass chrome coated valve. They're very heavy. You can feel them, that they're different. This is what you'll see often in this or stainless steel in very expensive regulators, very nice regulators. Then this is the same version of that in a an aluminum. Okay, so it's aluminum. It's a little lighter, still looks good, still works well, but it's aluminum body. And then you'll have aluminum bodies like this that are painted. They're painted. Better ones will be chromed or just left brushed. Regulator bodies may be forged of bar stock construction, formed from casting metal and mold under pressure. A bar stock body is made by machining out bar stock like this right here. You'll see that is square bar stock, and it's actually been machined on CNC machining setup to create. Sensing elements are the piston or diaphragm. So a piston is usually used because it's simple and it has less droop, which we'll explain later, and a diaphragm is more sensitive and finer regulation. That's the actual pressure as you turn one of these dials, or in a fixed unit where they're set, that's the actual pressure coming in. Diaphragm materials are constructed from neoprene, they're metal types, brass, as we spoke about earlier. Regulator accuracy and capacity. The accuracy of a pressure regulator is determined by charting outlet pressure versus the flow rate. The resulting graph shows a drop in outlet pressure as the flow rate increases. This phenomenon is known in the regulator industry as droop. Pressure regulator accuracy is defined as how much droop the device exhibits over a range of flows, while less droop equals greater accuracy. Droop can also be caused by significant changes in inlet pressure from the value when the regulator output was set. So we've all heard about pressure dumps or CO2 tank dumps in the aquariums, and that's what it's referencing. As the inlet pressure rises from the initial setting, the outlet pressure falls. Conversely, as the inlet pressure falls, the outlet pressure rises. Some models give a plus or minus accuracy on the outlet pressures. Some models have balanced poppets that can help have less droop and flow changes as pressure drops. Now, what does that graph and all of that mean? Well, the bottom line is the more accurate the regulator is in its design, whether they're using a balanced poppet design, a dual regulator design, or whatever, what we're looking for is one, no chance of tank dump. Now, in our test, we didn't see that was near the issue of that you read about online. So it's not usually, in these better regulators, it's not usually that big of an issue, and we'll explain that later in the testing. But more importantly, when you set the needle valve and you set your pressure to the needle valve, what we're looking for is it to stay where you left it. Now, all of these units tend to have like a 24-hour cycle where you got to go back and there's a break-in, and it seems to be that you have to come in and regulate them well, at least one more time, and then once you get it set, they're good. The better ones have less droop, so the pressure coming out of the first or the second stage, depending on the design, to what we're going to call the needle valve stage, which is also a stage, is more consistent. So if you came in with 20 psi, just for sake of a number, to this needle valve, and then you set it, okay, to 2 drops per second, again, just for reference. If the pressure changes from 20 to this needle valve, well, it's going to affect how fast these bubbles are working, and that's where you're constantly fidgeting with it. Things that can help that, most importantly, is design of the regulator itself, those inner workings. Secondly, the quality of that needle valve. And those are things you look for when you're looking for features in these. But that explains a little bit about how that works and why that matters. Single stage regulators. They look like this, or often even like this. They'll be sold to you like they're dual stage when they're really not. They're dual gauge, not dual stage. And even though the needle valve can be considered a stage, for the sake of this, we're not going to call it a stage. When you're talking about a dual stage regulator or a single stage regulator, it has one stage inside the regulator. Single stage regulators accomplish pressure reduction in a single step. Delivery pressure cannot be as tightly controlled as with a dual stage regulator. Unbalanced single stage regulators need more frequent adjustments than balanced single stage regulators. And more expensive single stage regulators use a poppet, a modified poppet, to reduce the effect of droop, as we talked about before, or that change in pressure. This part is very precisely machined, and there's a small, teeny little hole. So in a regular unbalanced regulator, you just have pressure coming in to the poppet. In a balanced one, there's O-rings and there's small little pinholes in the orifice. It's a more expensive design, but it will allow a single stage regulator to be highly effective for CO2 application without droop. An example of that is this unit here. It has a balanced poppet. Dual stage regulators. Again, not every dual stage regulator is necessarily good because it's dual stage, but the better dual stage regulators are the way to go for the most precise flow. Again, a balanced poppet regulator, often excellent and all you need. But if you want really precise flow, or you're doing a multi-port setup, or using systems that are for reactors, things of that nature, dual stage is better. Now let me explain what dual stage is. Essentially a true dual stage regulator, and there are some variations where they made some modifications, is 2 regulators in one. For sake of simplifying the numbers, so let's say you've got 100 psi coming in to your initial regulator and poppet. In a dual stage regulator, the first stage is going to drop that down to say 50 psi. So it's constantly holding at 50 psi like our fixed regulators like this. And then that 50 psi is going to hit the second regulator that's built in. And that one is usually an adjustable type. So you can adjust it, but you're adjusting from 0 to 50. Anytime you're adjusting or compensating from a lower psi range, the more accurate the regulator is. Now, safety is another part of that. There can be a leak between the 2 pressures, and better regulators will have, just like this, they'll have a safety valve and a bleed-off valve for those. But that's how a dual-stage regulator works. Other considerations for the different regulators. Usability. That's one of the first things we look at in these regulators. How easy is it to turn the dial? How easy is it to secure to the tank? How easy is it to rotate or use the valve? How well does it function? How quickly can I get it set up? That's an important, of course, with any of these. How complicated they are, and more importantly, how easy they are to regulate. Drift, we talked about that in the various stages. So we looked at all these regulators, how easy they hold their numbers when the power goes off, back on, when the solenoid cycles back on, when you set up the tank again over a week, how easy they are to keep regulated. Readability of the gauges. Some gauges are easy to read, some aren't. It may not be a deal breaker, but that's something we looked at and rated on all of these units. Safety. Safety has got to be number one. So the quality control of the regulator, whether it's the connection of the solenoid valve, and does that solenoid valve, is it water protected? Does it generate too much heat? How well the construction is, the material, the O-ring seals. Did it hold our pressure test overnight? Does it have a dump valve? Does it have a manual dump valve? Does it have safety valves checked in? What these valves do is if the pressure in the regulator somehow got too high or the regulator failed, these valves will dump. It also prevents you from ever, if you've got a valve at 100 psi, it prevents you from ever having to worry about this glass exploding because you messed up and there's too much down pressure going to one of these devices. So a dump valve, those are the types of things that you're looking for. Compatibility, accessories and compatibility. Now, again, the quality of the solenoid valves. Our test showed that some of these ran way too hot, hotter than we would like them to. Some of them didn't have good connectors and wires were exposed. Some of them just simply were too low a quality for you to consider. Others fell in the middle, of course, and then some of the better ones were actually higher voltage and they produced almost zero heat. Something else with the valves that you need to be aware of when you're using standard timers, there is something I'm going to call ghosting of the electricity on some of these power supplies. What we saw was there's enough power on these sensitive valves to not make them function properly. There's some sort of a droop, so be careful and check that. Turn the valves on and off. Most of the valves were, they turn the timers off and on. Make sure the valve performs as expected. It's not the fault of the valve we found. It was something to do with the timers. So make sure your timer works properly with the valve. Rotatable needle valves, how easy the needle valve is able to be turned. Those are features that you're looking at. What type of tank? Some of these are able to be used right out of the box. This particular little valve can be used with disposable cartridge, can be used with paintball adapters, and can be used with standard CO2 tanks from the US, either side or top mount. So you want to make sure the way you want to mount it, the type of tank you have, it's functional for you. Pressure regulators. Some of them have pressure regulators. 2 regulators. Always you get a regulator that shows you the tank side, or the outlet side, I should say, of it. Now here's what's interesting about that. CO2 is always going to show on your tank side regulator between 800 and 1,000. You can only get a true reading of CO2 by the weight of the tank before and after it has CO2, because CO2 goes in as a liquid. And when the liquid is gone, the pressure quickly goes from 800 to 1,000 to 0. And so that gauge lets you know there's stuff in the tank, but without feeling the tank and weight, it doesn't let you know how much. The second gauge is your outlet pressure, which you can have adjustable, and you can see that go up and down. There'll be a different range on those. And then, so some will be 0 to 60, some of them 0 to 120, depending on how the regulator's set. On those higher PSI regulators, those are the ones that you want to use, like this regulator here. These work well for some of the reactors that require higher PSI. Now we'll show that in the blog and all the specifics so you can read the specifics of those regulators. Output pressure adjustment. This is another thing to look at when you're buying the regulator. There's a range on here. For instance, the Up Aqua will go a lot higher PSI range than some of the other models which are fixed like 0 to 60. The thing you need to remember, you can, if you have these turned all the way up, which it's actually counter than what you think. Right is higher pressure, Left is looser pressure, not the other way around, or lower pressure. If you go right, you're increasing the pressure. You're not turning off the tank, you're increasing the pressure. If you turn it all the way up and then quickly surge a tank on, you can ping and screw up some of your gauges. So remember that, but look at that pressure range to see if it's in a range that's going to work for you. Lastly, the needle valve. Again, some of these rotate, some of these don't. They have bubble counters, some don't. The bubble counter's nice if it happens to work for the tank you've got, because you can see the bubbles initial setup underneath. I prefer still, as I've said in other videos, to be able to see up by my aquarium. I can just walk by without being in a cabinet and see that my bubble counter is working up in these type of bubble counters or in the unit itself. So I like both. But some of them have these built in, some of them don't. I don't think that's a deal breaker, but we do make note of that in our tests. Okay, now that we've gone through the basics of how these work and what actually happens through images and graphics, we're going to go into straight into our picks and start showing you the individual pics of the regulators and the function of them with some more video footage. Now remember, we're going to have a blog post for this that I'll put the link down below, and it'll give you instructions on hookup and go through literally everything we've talked about graphically in this video, along with some more safety and use. For instance, the different PSI ranges for the different valves, that'll be included there. And so everything will be overviewed in the blog. But right now, let's get right into these regulators, because one, it was fun to look at all these, and two, I think you're going to learn a lot about them and be able to pick the ones that you want. I know we were able to.